My name's John Gould, G3WKL. I've been leading the team that's put together this year's programme of centenary events. And before I introduce the next speaker, I'd really like to say a personal thanks to Bob Royal and his colleagues within the IT for his efforts in making this a reality. We were actually, when we met this evening, it's pretty well a year ago to the day that we started off seriously talking about this evening's event. So thank you very much, Bob, and the IT. It's my great pleasure to introduce Lee Hudson M0LMH. I first came across Lee in 2008 when his application for a license variation for a 501 kilohertz transmitter was passed to us for comment, passed to us in the RSGB for comment. It was shortly after that that Lee showed me his design and prototype of the 501 kilohertz transmitter. I have to say that Lee's design process was absolutely amazing and his construction immaculate. And I think, well, I really thought it was a commercial product, but apparently it was a prototype, and I wouldn't dare to show him any of my prototypes. So I think he rightly held by his friends as a commercial-grade constructor. Lee started his career in the late 1980s as an electronic engineer with Shorrock Security Systems before moving into CAD/CAM and DNC programming within the structural steel fabrication industry. An example of Lee's work can be seen in the 61,000-ton superstructure at Heathrow Terminal 5, which was fabricated using an autonomous CNC programming system that Lee designed. This year, Lee has returned as an electrical engineer with a move to Keytech and is now involved in communication, information and detection technologies for the transport and defence sectors. Lee's interest in amateur radio, like so many of us, came from his dad, who may be listening tonight, I don't know, or watching. He's online, so welcome, Dad, G3RFL, who's a keen ATV, amateur television enthusiast. At the age of 10, Lee gave a lecture to the whole of his primary school on how TV works, aided by his dad over an amateur TV feed. Lee was licensed in 2007, is a member of the RSGB, the British Amateur Television Club, and the highly successful Brim Contest Group. And I think you saw one of their aerials, the beverage in the snow. He's also an instructor and examination secretary with the Ripon and District Amateur Radio Society. Lee has given numerous technical presentations, including a lecture on electronic circuit simulation at last year's RSGB convention. Over to Lee.
Thank you, John. Welcome to this second lecture of the evening. I'm your presenter of a vision created by contributors from a number of subject experts in their own view on how amateur radio may develop over the next decade or so. My talk is structured in terms of technology drivers. Looking back over the past 100 years, we have shown ourselves as great appliers of technology, often in ways not originally envisaged by its creators. An amateur's relationship with technology and society is not immune from their changes over time. National and international communications probably attracted many of us to the hobby in the era before mobile phones and the internet, but not necessarily today. Technology, software and systems engineering, and the maturing of amateur radio as one of the original social networks is still providing attraction. It's perhaps worthwhile pondering comments made by Dud Charman, G6CJ, at his inaugural presidential address in 1952. Let's see over the next half hour whether his vision for a look 50 years ahead will be as valid today as it was in 1952. Let's start with component technology. I think that we are all familiar that traditional wire-ended components are on the way out, and as amateurs we are already challenged to having to adapt to using surface mount devices, or SMDs, and large-scale integrated circuits whereby complex and multiple functions containing millions of components are built into a surprisingly small package. With around 3 million amateurs worldwide and perhaps only 40% whom are really active at any one time, most will buy commercial equipment. We are only talking of a commercial market for a few 100,000 main station transceivers each year. With VLSI standardization, some amateur transceivers are increasingly likely in future years to be spin-offs from other products, with benefits of perhaps more transmit power and lower cost. Recent VHF and UHF handhelds are good examples of this trend, which could well see the complete radio on a single chip. But will the same benefits of mass production apply to our main station equipment where the relationship with non-amateur products is less obvious? Discrete components may largely give way to VLSI and commercial sub-assemblies that are integrated with software applications. Components will still be available, albeit as surface mount, and newer components, when available, will give superb performance. However, their availability will be based on the needs of mobile phone users and other consumer products. Chips designed for mobile phones are highly integrated and not always suitable for amateur applications. VLSI technology that underpins software-defined radio architecture in our mobile phones means that today we can buy a chip like the AD9957 for a few pounds. This is a multi-stage upsampling interpolator, quadrature modulator, numerically controlled oscillator with a complex mixer and a high-speed digital to analog converter. This is a typical device that offers great opportunities for software-defined radio in implementing a direct-to-RF digital exciter. Other LSI devices are available, such as the AD9653, which is a quad 16-bit 125 million samples a second ADC. With these and similar technology available today, we can look forward to very high performance direct sampling front ends for HF software-defined radios in the future. What else might we adopt from mobile phone technology? One suggestion might be to adapt the digitally controlled feedback loop amplifier. It should be easier at VHF and even more so at HF. The advantage will be better efficiency, cleaner outputs, and perhaps removing the need for passive filtering. The disadvantage is increased complexity, but at what point will the pros outweigh the cons? Adapting these to use of VLSI and constructing bespoke designs using surface mount is not easy. In terms of construction, it's all part of a technology that assumes mass automation, coupled with pick and place and reflow soldering. The technology is not ideal for one-offs, modifications or repair. Yet the way in which we have adapted to its use, with a small soldering iron, illuminated magnifying glass, tweezers, is probably all becoming a newly acquired skill for many. While surface mount has made home construction a bit more challenging, the design and development task has been made easier through a number of excellent circuit simulation, filter design, aerial modelling, computer applications and so on. This makes it possible to do serious design quickly and cheaply. Another VLSI building block is the field programmable gate array, so named as it is made in mass production for configuration by the original equipment manufacturer. Originally, FPGAs contained mostly logic functions, but the technology has moved to include analog features such as analog to digital and digital to analog converters, as well as other software configurable devices such as microprocessors. Climbing the learning curve to use these powerful devices is likely to be one of our challenges over the next decade. Much like the new electronic and computer technology, it is the province of specialists. However, the way forward for amateur radio is probably through open collaborative projects. This said, the current set of FPGA development tools include intellectual property blocks, IPs, that can be drag and dropped into a design with only a small amount of connectivity between blocks to be defined. IP blocks can range from peripheral serial ports, external memory interfaces, through to microcontrollers and MPEG decoders. This enables a high-level system approach which is much easier to learn and implement. Whilst on the same theme of collaborative projects, let's look briefly at a current one, the high-performance SDR project. This is where people with a range of different skills worked together to produce a state-of-the-art SDR transceiver. This collaborative venture started in 2005, where the participants applied their technical knowledge and experience to make some creative steps in radio technology. The picture on this slide shows the complexity of the HPSDR Hermes board, the receiver, transmitter, and Ethernet communication functions. Maybe this form of technical collaboration is today's analogy to the exploration that occurred by amateurs in the 1920s. Looking to the future, collaborative projects will increasingly see software becoming plug-and-play components, allowing different algorithms to be used for different subparts of the overall software package. We can expect more from our technical experimentation to be in the software that is embedded within the hardware modules, or as the previous slide hinted, within the FPGA itself. Aside from large construction projects, amateurs are also adapting existing technologies, such as developing apps that, with the addition of cheap DVB-T dongles, turn a smartphone into a broadband receiver, spectrum analyzer, or band monitor. Some amateurs are already experimenting with opening up DVB-T dongles themselves, cross-connecting the clocks to create directional arrays of receivers. Mass-produced dongles are so cheap they become a sub-assembly component in larger systems. Amateurs have a long-standing urge to break the warranty void if removed sticker, mainly from curiosity and interest as to what's inside. This usually heads to modifications that make technology more applicable for the amateur use and wasn't the intention of the original manufacturer. While discussing SDR and operating, the view that radio noise floor is gradually being eroded by various noise sources is of great concern for the future. Amateurs are always faced with the difficulties of erecting aerials, etc., in modern high-density housing estates, high-rise flats, and so on. Thus, there is a strong driver for remote stations to be constructed for more general use. The images in this slide show the basics of a remote station setup, which in this case was built to provide a remote moon bounce facility on 2 meters. The stacked Yagi aerials along with the software control panel can be seen in the lower image, whereas the right image is the distant control laptop and modem. This setup was used for an internal demonstration to Ofcom staff as one of this year's RSGB centenary events. Currently, there is a licensing restriction within the UK, but given sufficient discussions with our regulator and application of sensible control systems and processes, the use of remote transceiver stations amongst a club or group is likely to be one of the main developments that we can expect to see in the next few years. Removing receive systems to quiet rural locations and getting the transmission away from potentially causing interference in residential areas is something that many amateurs would value. Looking wider at the impact of software and computer technology, we have enormous capability at our fingertips compared with a few years ago, and Moore's law doesn't seem to be finished yet. This is not just in the main processors, but also in interfaces such as A to Ds, D to As, in sound cards, and the extensive software libraries for digital signal processing. It's envisaged that techniques will be developed to take advantage of the highly parallel processing nature of current and future microprocessor cores. Computing power has led to great facilities such as CW Skimmer, which replaces about 100 World War II voluntary interceptors by decoding multiple Morse transmissions in parallel. There's no reason why this shouldn't be extended to cover other digital modes or data modes, of which some have already been achieved. The biggest challenge would be implementing the same for voice modes using untrained multilingual speech recognition technology. Language translation tools have certainly been developing rapidly. This will become applicable to amateur radio, allowing two-way traffic in each operator's native language to occur, where automatic translation is performed at the receiving end. This may make the rubber stamp contact a thing of the past. Turning the same concept around the other way, today we have a remarkable training tool called Pilot Runner. This simulates the reception of multiple Morse signals within a small audio bandwidth, challenging the operator to pick one signal and communicate with it. The software does all the rest, but it will only go in the log if you get the call sign and station that you were trying to contact correct. Pilot Runner is just like operating in a real contest to some extent. Where are these operator tools and training aids going? Well, this seems commonplace with SSB or perhaps digital speech somewhere into our next decade. With today's computing power, we can run complex propagation prediction algorithms at home. But more than that, amateur ingenuity is also creating near real-time propagation visualization of frequency, time, and geographic distribution of the available stations. This is a huge big data opportunity where propagation prediction, solar and usage data is mashed together, the so-called era of predictive analytics. How are facilities like Whisper.net, LiveMUF and LiveCQ for EME contacts, band time, active histograms from contact aggregators such as Clublog going to develop? Looking more generally at propagation science of amateur radio, there have been great strides made in recent decades on our understanding of the probabilities related to anomalous propagation modes such as aurora, trans-equatorial propagation at 6 meters, and grey line propagation. But whilst the scientists uncover some of the mysteries of solar and plasma physics, there is still much that is an attractive field for the amateur who can combine theoretical knowledge with practical know-how. Perhaps for the future, we have a better ability to predict potential openings with more accuracy. For example, if the interplanetary magnetic field BZ goes south, the solar wind speed picks up and we have witnessed a coronal mass ejection event, this would suggest that a VHF aurora was more probable. Similar with grey line propagation, we may be close to refining better models to help predict grey line openings. Current experimentation is looking at the correlation between propagation enhancement on 160 and 80 meter bands around sunset and sunrise along the path with the reception of medium wave broadcasts. Let us turn to consider modulation and how the way in which we impart information on our transmissions may evolve. For many years, various forms of analog modulation has been the norm. True that SDR allows us to do this digitally, but to what extent is the next decade or perhaps to will digital become the norm? In the recent past, this development has been held back by issues over codecs, the component that cleverly converts analog speech into a compressed data stream and vice versa. There have been black boxes owned by equipment manufacturers. Recently, however, the development of amateur open source codec 2, offers both access for experimentation but also signal to noise and bandwidth advantages that may convince many of us to change from SSB. The interference caused by digital speech and SSB to each other means that the concept of technology neutrality can't apply. Thus, we may need to plan their use in different parts of our bands. The RSGB's approach to Ofcom's forthcoming VHF spectrum release is to bid for new spectrum where experimentation with digital speech, television and data modes can be done. Amateur television is one area of the hobby where there is real freedom to experiment with technology. The ATV community already embraced digital modes and as a result gained significant bandwidth efficiency, reducing the typical 16 MHz analog FM transmission down to 2 or 4 MHz using MPEG-2 coding and DVB-S modulation. They have developed digital solutions that bring the cost of equipment within the reach of the average amateur. ATV operators have realized the full potential of the internet, and most repeaters are streamed live for viewing around the world, including this lecture. Projects are already underway to link remote receiving sites and develop voting and aggregation systems to enable mesh receive networks for projects such as Ham TV from the International Space Station. And for the future, we see the development of narrower bandwidth systems enabling full frame rate video to be sent on VHF and even HF bands using the same SDR-type hardware, H.265 video codecs, and CPM-type modulation schemes. With weak signal working, very significant advances have been made in recent years, using techniques adapted from professional radio communicators. Modulation and coding is all done in software, with its benefits of fast development and easy adaptation, and optimization for particular applications. We can gain processing advantage by playing with bandwidth and information rate in Shannon's law, often with redundancy or repetition. Controversially, we are probably detecting rather than communicating, but no one can doubt that it's fun and we are experimenting, which is what amateur radio is about. Whilst Morse code is still in use for some aeronautical non-directional beacons, the future of Morse code is very much in the hands of the radio amateur enthusiast. Despite the code being dropped as a requirement for the amateur license in most countries, this graph of 3 most popular modes in use on the amateur bands suggests that Morse code is holding its own. Clublog is, though, a special database that attracts electronic logs from those who focus on working distant stations, often in countries that have little or no resident amateur radio activity. It also contains many contest logs. That said, it's a reasonable statistic drawn from over 190 million contacts, or QSOs. The question is for the future: will amateur radio prove a good custodian for the art of Morse code? At the RSGB centenary dinner in early July this year, Professor Peter Cochrane gave an after-dinner address in which he took a look at the future of and postulated a spread spectrum world where instead of jostling for small pieces of bandwidth within a band, we instead all compete with mutually orthogonal codes with a direct sequence spread spectrum frequency time space. There are, of course, a few issues with this proposal, but in terms of futurist view, these are just the challenges that maybe amateurs will successfully adapt and overcome. In terms of spectral efficiency, band occupancy would change from being measured in terms of time and bandwidth gaps across the band to a measure of signal-to-noise margin for further DSSS transmissions across perhaps a much wider range of frequencies than that currently allocated to the amateur services. Will something like this be the way the future looks? Apart from the regulatory issues, we will need to address the orthogonality of coding that provides separation to the different transmissions occupying the same bandwidth, as well as understanding how to make our aerial systems more broadband, and also overcome the work within propagation issues such as multipath and Doppler. Microwave technology is developing fast, as is the rush for spectrum to meet consumer demand. Despite pressure on their microwave allocations, amateurs can expect to benefit from the availability of suitable components such as semiconductors, high QSO filters, short-range radar subassemblies, microelectromechanical systems or MEMS, resonators, etc., as spin-offs from a wide range of telecommunications and vehicle applications. Amateur satellite can be expected to continue and grow in popularity, especially amongst those outside mainstream amateur radio, as it couples radio communication with remote sensing. As Peter has already mentioned, we are all delighted with the successful launch on 21st of November of the first UK homegrown satellite, FunCube 1, built by AMSAT UK. As a companion project, the FunCube dongle was designed by Howard Long, G6LVB, for primary school and secondary school children to monitor telemetry data from FunCube 1 in order to compare data from reference experiments in the classroom with those from the satellite. Radio amateurs are continuing to extend their presence on the International Space Station with the addition of an amateur digital television transmitter to one of the 2 amateur radio stations on the ISS. In terms of satellites, perhaps the next 10 to 20 years, with improvements in satellite propulsion, we can expect higher orbits to be obtained, along with perhaps an amateur geostationary satellite, and also maybe orbiters around the Moon or Mars. Turning to amateur interest in bouncing signals off our natural satellite, the Moon, The main issue of overcoming path loss will continue to be a challenge. Currently, in amateur optical communications, visible red, up to 120 kilometre paths have been worked on baseband and subcarrier systems at night, with surprisingly 100 kilometres reached during the day. Transmission modes are typically Class A modulation or Class B, with the use of audio being carried on FM or sideband carriers. Short-range optical transmission of fast-scan television has been demonstrated by members of the British Amateur Television Club, and no doubt developments will increase the distance further. For the future, non-specular reflection and refraction are likely to be an area of development, as this is working in the infrared, where silicon photo detectors are at their peak response and no visual disturbance is created. Contesting and DX operating, the pursuit of distant stations, often in countries of islands where there are few or no resident amateurs, has, over the past decades, seen huge attention to the design and operation from a systems viewpoint. The competitive element, coupled with the operator's inherent skill, has meant significant use of computer and internet technology to home perfection. Professional HF usage is down dramatically compared with 25 years ago, and with that comes less professional expertise. EMC concerns associated with this decline, and perhaps the decline in practical experience of the regulators, our urban world is full of RF noisy devices. Will advances in chip design and power conversion efficiency reduce or reverse this EMC decline? Potentially yes, but not without involvement of regulatory and engineering skills. Maybe Doug Charman's prediction in 1952 for the turn of the century wasn't too far off the mark, but perhaps less so looking ahead another 50 years from today. With the wider technology base of today that adds software and more systems engineering to hardware, along with the paradigm shift with global society, innovation in amateur radio can be expected to continue, but against a different background. Maybe today's radio amateur will be interpreted in a broader sense in the near future, as the innovation in amateur aspect of radio communication is shared with more people who have software and systems engineering interests and skills. Whilst the professionals surge ahead with mobile broadband, automotive applications and so on at microwave, amateurs are now often in the lead in application on know-how at HF. Open-ended innovation is what amateur radio is about. We have a unique ability to do this in many parts of the radio spectrum, more or less unconstrained by government or commercial interest. Long may that continue.